Having spent quite a bit of time on particle equilibrium, we now like to turn our attention to rigid body equilibrium. Before we do that, however, we need to understand more fully how eccentric forces impart rotation. We first discuss the moment of a force about a point. A moment about a point is calculated as the cross product of a position vector and a force vector, so the result is also a vector. We then discuss the moment of a force about a line. The latter is required when there is a hinge or other natural axis about which an object can rotate. To find this, we'll pick a point on the line and begin by taking the moment about that point. Because the moment is a vector, it isn't necessarily aligned with the hinged axis, so only a fraction of the moment tends to impart rotation about that hinge. We will need to take the dot product between a unit vector along the hinge and the moment to find how much of the moment tends to impart rotation about the hinged axis. We then discuss something called a couple, or a force couple, that produces a pure moment load. Finally, we close with a discussion of equivalent force systems. This last topic will turn out to be quite important to us because it provides a way to reduce complicated force distributions to their simplest possible forms. The moment of a force is a measure of the force's ability to produce rotation about a set of axes through a particular point. It is defined as m equals r cross f. In this expression, r is the position vector from the point of interest to some location on the line of action of the force. We will see that it doesn't matter what location on the force's line of action we choose. We'll get the same result no matter what we pick. Given the anti-commutative nature of the cross product, it is critical that the position vector appear first in the cross product operation. And because it is defined from a cross product, the moment is a vector. That said, there are some instances where we can use something called the scalar approach to find the magnitude of the cross product without actually using the cross product operation. This turns out to be most useful in two-dimensional problems where both the position vector and the force vector are in the xy plane. Under these conditions, we know that the moment is in the out of plane, that is to say the z direction, and so there is no ambiguity about the direction of m. It is either up or down relative to an xy plane on your paper. Even when we use the scalar approach to calculate a moment's magnitude, we need to keep in mind that the moment is always a vector. To get an appreciation of the vector nature of a moment, consider a worker loosening a pipe fitting with a wrench. We will want to know what moments are exerted at the wall where the pipe is mated to the fitting through a threaded fastener. Let's call this point O. Then we'll construct a position vector from O to the worker's hand where he is applying the force F. I'll sketch an XYZ coordinate system on the figure so we can evaluate the moment M. Note the position vector has two components in the XY plane, a length L along the x-axis from O to where the wrench jaws grip the pipe, and a length scalar r in the minus y direction from the pipe's jaws to the worker's application of the force on the wrench handle. Using our cross product properties, we have m equals r cross f which is equal to Li minus scalar rj crossed into minus f in the k direction. We can write that as minus fl I cross k plus fr j cross k, which is equal to flj plus fri. I've sketched these two components at O. The component along J represents the extent to which the worker is bending the pipe about its support at O. The component along I represents the extent to which the worker is loosening the pipe about its threaded axis. If the goal is to loosen the pipe without causing the pipe to bend at its threaded end, our recommendation would be for the worker to grip the pipe closer to its support at O. We can see the combination of these two effects with this brief video. Note the combination of bending and twisting as he applies a force to the end of the wrench's handle. This brings up another point related to terminology. What is the difference between a moment and a torque? This may not be an exact definition, but a moment is a load that tends to impart rotation. If the rotation is parallel to a long axis intended to admit rotation, the moment is a torque or twisting moment. If the rotation is perpendicular to an axis intended to admit rotation, the moment is a bending moment. In the present illustration, the FR component along I is a torque, and the FL component along J is a bending moment. If we wanted to loosen the pipe more easily while minimizing the bending, we could simultaneously increase F, use a longer wrench, which would increase R, and grip the pipe closer to O, which would minimize L. Even though a moment is a vector, we will talk about evaluating the moment using both a scalar approach and a vector approach. When we say that we are evaluating the moment using a scalar approach, we really mean that we are evaluating the moment magnitude using a scalar approach. This is most useful in 2D problems where both position and force vector are in the xy plane, and we know that the moment is in the plus or minus z direction. Imagine the shaded plane shown in the figure is in the xy plane. We identify the perpendicular, that is the shortest distance d, between O and the line of action of F. The moment magnitude using the scalar approach is the product F and D. The direction of the moment still has to be evaluated using the right-hand rule. In this case, we could slide R out and cross it into F, and our thumb would give us the direction of the moment, which would be as shown here. If you are uncomfortable with the scalar approach, you can always fall back to the vector approach. This slide is particularly useful because it demonstrates that it doesn't matter where on the line of action of F the position vector lands. I have drawn first a position vector R1. Recall that the magnitude of a cross product is RF sine theta, where theta is the angle between R and F laid tail to tail. Here I have sketched theta 1 in the figure. R1 theta 1 would be the same perpendicular distance d that I had for the scalar approach on the previous slide. If I consider now a second R2 to a different location on F, the angle theta 2 between R2 and F would be here. So both R2 and theta 2 would be different, but R2 sine theta 2 would still be this same perpendicular distance d that we used in the scalar approach on the previous slide. It doesn't matter where I choose to intercept the line of action, because even though the magnitudes of R and theta are changing with the intercept point, the product R sine theta still yields d, the perpendicular distance between O and the line of action of F that we used in the scalar approach. The advantage of the vector approach is that, having identified R and F, we can just turn the crank of vector mechanics we described in Chapter 2, so you don't have to use the right-hand rule to identify the direction of M. This is particularly useful in three-dimensional problems. My general advice would be to use the scalar approach for 2D problems and to always default to the vector approach in a 3D problem. Of the comments in this slide, the most important is the first one. Do not evaluate the moment as F cross R, as your calculated value will be directed opposite to the actual direction. Always evaluate the moment M as r cross f.